Hey everyone, this is Benjamin from the Zephyr project. This is it, that time of the year, well, multiple times a year actually. A new Zephyr release is out, Zephyr 3.7. We are right in the middle of the summer 2024 when I'm recording this video, just a few days, literally a couple days ahead of the actual release at the end of the month, at the end of July. And Zephyr 3.7, before we dive into some of the interesting new features like we always do, one thing that's special about this release is that it's a new long-term support release. Every 2.5 years, typically, we do release a new LTS, long-term support. What does that mean? There is a lot that's happening in the Zephyr project. Every 4 months, a new release comes out with new features, deprecated features being dropped potentially. That's the way it works. Like, we want to keep the project going. But if you're building a product, this probably and most likely goes way too fast for you, right? When you're building a product, the life cycle and the development cycles are typically way longer than 4 months, and you don't want to build your product on an ever-moving target, right? You'd rather use something that's more stable. Arguably, it will be getting no new features, but at least it's stable. And should there be any security vulnerabilities, they would be addressed, just like, I mean, the same way it works with any long-term support release in the desktop or server operating system world, or any product really. So you're going to be building on a way more stable foundation, which is exactly what Zephyr is all about. That being said, there's actually quite a few new things that came and went into Zephyr, so we will be diving into those. On the topic of security, though, before we move on and switch gears, one thing that is worth mentioning, and it's actually quite unique in the open source RTOS world, is that we have our own security team, and whenever security researchers or anyone really reports security vulnerabilities, we do all the assessments and we disclose the vulnerabilities responsibly to potentially to users and customers, which might be you. And so one thing that's worth calling out is our product creators vulnerability alert registry, which you can subscribe to as a product maker. You can find the link on the Zephyr website, and any vulnerability before being publicly disclosed, you can get looped in and get a chance of addressing and deploying the fixes that we will be making available to you in a more sort of like responsible manner, and you get to fix the issues ASAP. So it's actually quite independent of the whole LTS story. It applies to virtually any release impacted by a security vulnerability. What's unique about LTS, though, is that should there be, like 2 years down the road, a security vulnerability affecting the LTS, although it will be quite old by that time, we will still be making the work to deploy the security fix and make it available to this branch, to this particular version of the project. So that's for security, that's for LTS in general. I think in the release notes, actually, we do spend some time going through some of the high-level changes. I mean, if you've been using the previous LTS, I mean, it will feel like a really like a kind of like a brand new car almost for you. Zephyr 3.x gets quite a new changes and features as opposed to the previous version. But here you get a high-level overview. You're of course encouraged to look at each release notes of all the 3.x versions to get more details. But as you've seen in the past few months, we've been talking about some of like the news in 3.5, 3.6, etc., GNSS support and like battery chargers, whatnot. I mean, you might know about some of those changes already. Back to 3.7. There's quite a lot that went into the release. There's a blog post that accompanies this particular video, well, and the other way around. If you're reading the blog post, the video will be a great complement as well. Going through some of the details more in text as opposed to watching some demos, which this video is all about. So read through the entire release notes if you care about like some specific architectures, specific drivers, specific bugs that you were hoping would be getting fixed. It's very likely that there's a mention about them in the notes. But at a high level, some of the interesting, noteworthy, cool changes are listed here. Starting with, I don't think I will be having a demo per se. There's actually an interesting tech talk that you may want to, and I will be putting the link somewhere so that you can check it out in more details. But over the years, Zephyr has evolved, but so has the embedded industry, right? And nowadays, you will find more and more often SoCs that are effectively, I mean, it's not just one core, it's multiple cores, like just like we see in the CPU world, I guess. But yeah, multiple cores. It's actually also quite common that those cores are not even the same architecture. You would have an ARM Cortex-M core sitting alongside a RISC-V core. You would have boards and designs basically where you end up deploying multiple SoCs, right? Because you want to address different power, you're targeting different power management capabilities for different functionality of your system. So you will have a small MCU alongside a bigger MCU. Maybe the small one is like a good old, very simple single core architecture. The more complex one is going to be more complex. I mean, you get the point. So the idea is that there is now a new Zephyr, a new hardware model in Zephyr. By hardware model, what we mean is basically what allows you to describe on top of the good old device tree, what allows you to describe your actual system in terms of what makes up your board, like your pretty much your device in a sense. And there's plenty of documentation. Again, I don't have a demo per se, but you will see in the demos that I will start using the new hardware model for those boards that effectively leverage it, which is a majority of the boards in the Zephyr tree. But really briefly, I guess we can look at this guy here, where in the past, typically when building the good old West build command, when building for a particular board, you would just bother about knowing and indicating the name, the identifier of the board, real board, BL5340, whatever. Potentially your board had a revision, but should there be more to it than just a board, a single SoC, a single core? Now, basically the board target can be something more complex, right? And you can add to the full identifier, if you will, the full naming scheme, things like the actual SoC that you're targeting. Should the SoC have multiple cores, CPU clusters, you would be looking at that as well. Variants, like the secure, non-secure variant. So that's what's changed. So in practice, for you as a user, it means a couple of things. You're highly encouraged if you have like your own out of tree, like downstream description of what your actual, like you have your own board and your own design that you've described using the legacy model. You might want to look at actually adopting the new terminology and the new concepts from the new hardware model. And something else that might sort of impact you is, should you be building some of your prototypes or even maybe commercial products by means of extending the official Zephyr boards using your own configuration and device tree overlays. Those would need to be essentially renamed, right, to adopt the new board terminology, and maybe some configuration files here and there, and YAML files might need some massive search and replace sort of approach. There is, I think, somewhere right here, kind of like at the top of the documentation page regarding the new hardware model, some pointers. Like, well, what I just described regarding what you would need to do should you have board downstreams. And there's also a pointer to a script that you may want to use to save some time as well. So you might want to have a look at this one. We've sort of used it when dog fooding or when doing the actual conversion of all the Zephyr boards. This is a script that's proved quite useful, so it might be useful to you too. So that's for hardware model V2, and again, you will see some of it in the demos, and you're highly encouraged to check out the tech talks. Now, which one should we pick in this list? I will not be going in any, I don't think the order of all those demos actually matter. There might actually even be some like hotcuts in between the demos. So please bear with me if the transitions feel a bit harsh. But the bottom line is every demo, I think, is showing some really, really neat, cool features. So the first demo is going to dive into some networking topics, and more specifically, there is an addition to the Zephyr 3.7, which is the implementation of the Precision Time Protocol, PTP, and IEEE standard, which is something that's really relevant if you're looking at use cases and scenarios like industrial automation, industrial IoT, where you have several devices on your shop floor that are all measuring, sensing what's happening with your machines and your industrial equipment, and gathering the data, uploading it to some kind of edge gateway or some server. But this data, when the physical events actually occurred, is really important, and you want to capture that information with the highest possible precision. And for that, you want to make sure that all your devices share the same reference and have the same wall clock, if you will. And so that's exactly what PTP allows. You may be familiar with things like the network time protocol, which is an alternative and allows to get some kind of reference, but usually you get in the realm of millisecond sort of precision, which PTP goes way like far beyond, and you can reach sub-microsecond. It has lots of cool tricks to take into account the latency of your network and things like that. But that's that's something that's now available in Zephyr, and I've decided to show you a demo where I'm combining it with another really interesting addition to the Zephyr tree, which is a new code sample. And we have, as you probably know, we have tons and tons of samples, but most of the time, those code samples are very much self-contained, if you will, like really basic functionality that's being demonstrated. Whereas now, and I hope we will be getting more of those, we have code samples such as this guy, the secure MQTT sensor and actuator, that demonstrate a lot more. If you look at this sample and try and use it on your board, granted that you have some kind of sensor and a network adapter, then it shows you how to configure the Zephyr networking subsystem to get auto IP address from a DHCP server. It shows you how to connect to an MQTT broker and send data to it, subscribe to the broker, implement and do so over TLS should you want to and care about secured connection, synchronize the have the network status reflected on an LED. I mean, really lots of cool best practices being demonstrated in the code sample. So what I did is I took a bunch of devices and ran the sample on them, except that I augmented the sample with PTP capabilities. So where out of the box the code sample would be every, I think, 3 seconds, read temperature data from a thermometer and send the data to an MQTT server, and it reaches the server when it reaches it. Now I've added and tweaked the code so that we get the time information from the PTP clock. So that is more specifically from the network adapter. Like PTP, as soon as you enable it, will be taking care of synchronizing the clock against a grandmaster clock in your network, which in my case is a Raspberry Pi that I have on my network, and then synchronizes the clock against it. And so yeah, the sample does just that, like where historically it would have just not cared at all about timestamping the data. Now it does using the PTP time information. Let's see a short demo to see what I mean by that. So quick recap maybe of the devices at play. We have an STM32F7, another STM32F7 right here, respectively a discovery board and a Nucleo board. We have, and this is going to be important for the rest of the demo, this guy right here is actually is not a Zephyr device. It's a Linux based device. It's a Raspberry Pi Compute Module 4, which will be participating in the demo. It also synchronizes its clock, its system clock, to the PTP Grandmaster. And so yeah, all those devices are all going to talk MQTT, all going to send data, and hopefully we will try and see whether the data seems to be using the same time reference. And the other thing you don't see on the video or on the screen is a Raspberry Pi 5, this time around, also running Linux. And it's the one guy running the Grandmaster clock. So all the other participants to the network, they all have a PTP client. Those guys would be a Zephyr, right? A Zephyr, the new PTP subsystem. This guy has a Linux-based PTP client, and they synchronize against the master clock. So the two STM32 boards are publishing data to the MQTT broker. So let's see. It's actually also running on the Raspberry Pi 5. Let's connect to it. Do we see any data just yet? We do not, because the boards, the STM32 boards, are not powered, but there seems to be some data still. That's because I wrote some basic Python code running on the Raspberry Pi Compute Module 4, so that it also sends telemetry to the cloud and to the MQTT broker. In this case, it's sending its CPU temperature every now and then. So yeah, and this, I think you can get where I'm going with this. At some point, we will have 3 devices, all powered, all synchronized against the same clock, and we want to figure out whether they seem to be using the same time reference. So let's power on this guy over here. I don't know if you see the LED, but I just pushed the USB power cable right into the device. So let's see if they start showing up. The Nucleo, the white one, is the first that I powered, so it's no surprise it showed up first. Then we have the discovery kit, and well, things seems to be in order. What one thing you may have seen is both STM32 dev kits both have a temperature sensor attached to them. So what if I put my finger on both sensors? Yeah, we have, I mean, real-time telemetry, right? That's the whole point. And so given that the temperature is being sent with nanosecond precision, it means that should we want to consolidate this data, measuring the same physical event and like make sure that it's all aligned, we would be able to do so. However, both boards, they send data every 3 seconds, so we don't really know whether they're effectively synchronized. So one way to double check whether we reached microsecond sort of precision is that I have something else in the demo. I have a push button right here. This push button is hooked up to all 3 devices you see on the screen. 2 of them are Zephyr based, and one is my Linux Compute Module 4 device with a Python based simple script running on it. As soon as I will press the button, all 3 devices will be capturing the data, timestamping it really accurately, send it when they send it. It actually doesn't really matter because there will be lots of network latency. There might be latency in the actual networking stack based on how the Zephyr scheduler behaves. I don't really care at the end of the day, because the timestamping should be allowing me to know when the event physically occurred and really occurred. Let's press the button. All right, Raspberry Pi sent the event pretty much immediately, and all and the others they're only communicating every 3 seconds, so it took them slightly longer. Let's just filter out the data so that we're slightly less polluted visually. Let's see, we have the Raspberry Pi who supposedly picked up the GPIO event. I mean, every one of the devices, they all picked everything in the same second, apparently within the same millisecond as well, like 514, those are milliseconds we're looking at. And then we have 758 right here, 894, 823. So it looks like we were within 100 microseconds, which is all right. I think we can do better. Let's see. Maybe the clocks were not fully synchronized just yet because it might take a while. I mean, the clocks need to stabilize. They're both synchronized and syntonized. So if the frequencies don't match, it takes a while to adjust, and the devices have been powered only for a minute or so. But now I think it's actually looking better. We have 078 right here, 145, 125. So I think that means that we are more or less within what, 70, 80 microseconds, which is really impressive, right? Because that means that should the physical events that I want to capture are like really high frequency vibrations and things like that, like even looking at like over like thousands of hertz, basically, I would be able to line everything up. When I do my data consolidation behind my MQTT broker, I will have some time series database and whatnot. I will be able to line things up quite nicely. So that's pretty impressive, I think, to have this kind of feature now being available to Zephyr developers. It does require to really get the most of PTP. You do require some support from your hardware. The Ethernet MAC controller needs to be able to do what's called hardware timestamping. So because you want to like be able to timestamp the data as it's actually going on the wire to work around all the limitations of and all the latency that could be introduced by the scheduler, the networking stack and whatnot. But STM32 microchip NXP, if you look in the Zephyr tree, lots of drivers are actually available and implementing PTP already. If you are a vendor that does that has Ethernet as part of your SoCs and haven't looked into implementing PTP support, you might want to do that to enable those kind of scenarios. So yeah, that's for the PTP demo. I could have shown the code, but really what I changed to the MQTT actuator demo is not much really. Enabling PTP, there is a kconfig that allows to enable the PTP clock drivers and the PTP subsystem. And as soon as you do that, a new thread starts running in the background and look for other clocks on the network to synchronize against. And then as I have this PTP agent or thread running in the background, whenever I need to get the accurate clock, I just use the PTP clock driver to get that time information down to the nanosecond. And as you saw, it's pretty impressive. One last thing in the MQTT example, MQTT is obviously a publish-subscribe protocol. So one thing that I could do is try and talk to the blue board, the discovery kit, and send commands so that it toggles LEDs on and off. Yeah, you should be able to see it right here, right? I can send commands, and so that's also something that the samples shows you how to do the right way, right? By having all the by designing all your different threads and message queues and whatnot, so that you're doing everything in the most sort of idiomatic way. And yeah, that's it for PTP. One of the, I spent a lot of time putting this demo together, but this is one of the really exciting new features in 3.7 in my opinion. All right, another networking sort of related piece of news, long-awaited. It says right here, long-awaited, and that's very much the case. There's, until 3.7, Zephyr didn't really have a really good story when it comes to providing a way for people to expose HTTP resources and create HTTP servers. HTTP client has been there for quite a while. We used to have an HTTP server external library in the past, but it got dropped at some point. With the new HTTP server library, you essentially have a really nice high-level set of APIs to expose HTTP resources in your application, and building on the rock-solid Zephyr networking stack. It means that adding TLS support, for example, and doing HTTPS, I mean, it just works. It's just a matter of enabling TLS in your networking stack, pretty much. And the HTTP server supports HTTP 1 and 2, HTTP 1.1 and HTTP 2, which can be quite interesting for constrained environments. And it also supports WebSockets. In the context of this video and in the demo I've put together is pretty straightforward, building on the existing HTTP server code sample, which has, like as you can see in the main file, you can see how the typical macros look like when it comes to declaring resources. A classical HTTP resource, which in this case apparently will be mounted at this particular URL or URI when you hit /dynamic on the HTTP server, either over an HTTP GET or an HTTP POST. It will be this particular callback that will be in charge of replying to the HTTP client. And similarly for WebSockets, you have an easy way to declare HTTP resources that are effectively WebSockets. In this case, there will be a dedicated callback and handler, which is where I did some tweaks so that it exposes sensor data, right? And so I'm set up my environment so that all the changes I made to the classical sample should show up, but basically pulling in the sensor API and sensor drivers to look at my at the accelerometer on my board. Hopefully there's one, and then when I'm in the WebSocket, when a client connects to the WebSocket, this is where I start sort of accessing the sensor indefinitely, so that I stream the sensor data to the HTTP client on the other side over WebSockets. So really just basic sensor driver calls and the new WebSocket API, where basically I push some raw text, raw data into the WebSocket in the form of JSON, which I am crafting here the quick and dirty way. I could certainly use the JSON library for that. But that's more or less the app, and so every 20 milliseconds it would push the data. And so yeah, the app, if I flash it on this guy over here, an ESP32 M5 stack, and we're going to actually switch real quick to the actual code on the client side. Like I've basically pulled together an app, which I should actually show you first. This is the app where I'm actually going to refresh so that you see that it's live. It's connecting to the HTTP server over WebSockets, and should I shake it up, you see all the accelerometer data. I don't remember whether it's X, Y, or Z axis, but you get the idea. If I flip it around, you see the data in real time at like 50 Hertz, which is, I mean, it's quite nice. It basically just works, and the code on the client side is just like really basic JavaScript relying on some random third-party library, where I effectively connect to the WebSocket to the server. So this is my ESP32 running Zephyr. I connect to it, and whenever the WebSocket has new data frames to push to me, I'm trying to parse them as JSON, and this particular this ends up becoming the last sensor value variable, which I end up putting like every 20 milliseconds. I refresh the graph And luckily there's new data available every 20 milliseconds, which I show on the graph. So that's yeah, one thing that you can do with the new HTTP server, but there's certainly way more that could be done. It's able to expose both dynamic resources, like, I mean, WebSockets would typically be very much dynamic by nature, but this could also be just regular HTTP resources, which you access over get post sort of interactions. Or this could be static resources as well. More think about them more as like you want to serve some web pages, HTML pages. The bulk of the content is likely something that you have somewhere in Flash, and you can use the HTTP server library APIs to register those kind of resources as well. So yeah, one additional cool news from 3.7. All right, so I want to actually use the opportunity of having this M5 stack device still handy to show a quick demo of something that's not necessarily called out in the highlights of the release. We need to scroll way down. This is where you realize there's so much. We need to go down, yeah, right here. I want to actually show you what I believe is one of the strengths of Zephyr, which is the device model it's being built on top of, and how the device tree basically allows you to potentially chain the devices to one another. What I mean by that is that historically in Zephyr, we've had for several years a driver for controlling LED strips. You know, those fancy RGB LEDs that are like lined up on a strip. Those chains of LEDs for which you expect a driver to allow you to control the nth LED on the strip, right? And so that's something that's existed for many years. On the other hand, there's also something that's existed for many years, which is the ability in Zephyr to have a standard API to interact with displays, right? Thinking like, I want to light up a particular pixel X, Y on a particular color. I want to use something like LVGL potentially to make the most of like my graphical capabilities. But one thing that the new LED strip matrix driver does is that basically this app that I have right here, it's actually something that comes straight from the Zephyr repo. There is like this accelerometer data that's being displayed here. When I move it around, I see like live data, and so this is built using standard LVGL graphical components, and the output of the GUI is the default display that I have on my device. With the new driver, which we're going to see in our device tree, what this is basically doing is that we're chaining, like I was saying before, like stacking up all the device drivers potentially to one another. In my device tree, what I've defined, and this is using an historical driver, there's nothing new there. I'm describing an LED strip. Like in practice, this guy right here, it's effectively 256 LEDs lined up. I think it's actually going in like a snake sort of pattern, but all I care is that I will be hooking up to a particular GPIO of my device. I will be hooking up this LED strip, and potentially I can use the LED strip node in my code to manipulate the LED strip using the standard LED strip API. So that's one thing. But there's a new driver now allows you to describe, given a particular LED strip, should the physical layout of the LED strip actually correspond to something that's very much a display, right? XY, you have a square of 16 by 16 pixels. Really easily, you can just like piggyback and tap into the existing LED strip definition. The only thing you need to declare is the the actual physical layout, right? And in my case, this would be again 16 by 16 pixels. You describe whether, whether the LEDs in your particular physical layout, whether they go like a serpentine sort of pattern, or whether it's more like one line, then the other, then the other. But I mean, you get the idea. And once you've done that, effectively, you have an LED, like the LED strip matrix compatible is effectively like any other display driver. And so the code that you were seeing just here, where the display output for my my accelerometer chart application would be the standard display, the standard LCD display. Now I'm going to change which default display I want to use in my app, save my overlay, recompile and reflash, and this should be pretty fun. In the meantime, I guess I should plug in the screen, or like the LED matrix rather, and let's see. All right, this is it. Let's see. Let's make sure this is visible. I'm actually going to maybe, yeah, slightly better. This is really like the exact same GUI as before. If I shake my device around, maybe I should do it more slowly, slightly flipping it around. I don't know about you, but I think this is really cool because there's literally nothing at all that changed in the code. It's really just a matter of reconfiguring the hardware and having also drivers that sort of tap and build on top of one another, which I find really cool. Yeah, so that's for this small digression on all things device tree, with a really good example. And there's actually quite a few other drivers that are having the same approach, and I encourage you to just like think about this kind of pattern when it comes to designing your own drivers as well. Moving on, do you remember from previous release from Zephyr 3.6, LLEXT, or linkable loadable extensions? A way to load dynamically at runtime binary ELF files that are code that you want to run and load at runtime. I like to think of them as plugins. You have maybe a graphical user interface for which, when you click somewhere, you want to like load something, and that something might depend on a variety of things and might change at runtime. So you want to load GUI bits from an SD card or from the network, whatever. And so you may remember this demo from Zephyr 3.6, where using LDGL, like I often do, I was showing how you can have a GUI where I click a button and it tries and tap into LLEXT subsystem and try and load and find an extension. The code really, and I haven't changed the code at all in the demo, is whenever I click on the button, I ask LLEXT whether there is an extension that goes by the name GUI_ext, and if yes, then I try and call the fill window function on it. So that's what you see just here on the demo. When I try and click on the button, it says that no extension is loaded, but extensions are easy to create. And actually, at the time, the extensions that I wanted to demonstrate, I was hosting them right in the same application and right in the same source tree, if you will, which is certainly really convenient, and building them was really easy as well. Like I had, as part of my Zephyr build system, I could really easily build new LEX targets and stuff. But I mean, maybe my main application, my core host application is very much proprietary, right? The customers, when they are gonna create extensions to my base application, I don't really want to give them access to my application, and frankly, I probably don't even want to give them or ask them to set up a full-blown Zephyr development environment if all I want them to do is really just implement some basic hooks for my definition of what a plugin to my system is. And that's where the new LLEXT EDK comes in. Where is it? Right here. So we're talking about something new in Zephyr 3.7 that is basically a way to ask West and ask your build system, knowing your host application and the way it's being configured and how it can and should be compiled, capturing, building an SDK, an archive really, that captures all that's needed to build extensions in a way that's like really portable, and that makes it easy for third parties to build extensions. And so what I want to demo is how, well, first building on top of the application that I had, like the application that you see running right here on the STM32 is has just been compiled. But if I am to call the build target, the LLEXT EDK build target, we're going to generate an archive that's like I just described, right? So let's build it, and then we're going to move on and use and set up a new brand new development environment for building our extensions. And the Zephyr 3 and the Zephyr SDK won't even be involved. It's going to be just like regular, if you will, regular C development. So let's build the EDK. All right, EDK is there. What is the EDK? Again, this is really just an archive. Like if we look somewhere in our build folder, we should see an archive, a tarball file, which is about 2 megabytes of header files, compilation flags. We'll see in a bit how to actually use it. And for using it, what I want to show you is how to start from, again, a vanilla development environment in the form of a brand new vanilla Ubuntu container, in which I have literally nothing file system wise. I don't even have a way to develop C code in there, so I need to install, and we're going to try and do everything in real time. I will need to install my basic tools for CMake. I will need Git, I will need wget. I need to be able to unpack the LLEXT extension developer kit. So I will need that guy as well. And XSD, we'll see why. You may actually remember from the previous demo. We have about 400 megabytes of stuff to install, which is not too bad. It's actually going pretty fast. So I'm going to have an environment that allows me to build C applications. What I don't have just yet in my vanilla Ubuntu machine is a toolchain to target the ARM CPU that's running on my STM32 dev kit. So I need that. So for that, I can have a quick look at the Zephyr SDK release page. And usually what folks do when they set up Zephyr development environment is they get a full-blown SDK, which gives them all the tool chains for all the architectures that they may ever consider targeting. In my case, what I really only need is the very small subset of the SDK that is effectively the tool chain for ARM. So let's copy the URL to this guy. Let's get that particular toolchain archive. We're looking at about 100 megabytes, 94 megabytes. That's quite fast to download. I'm gonna unpack it somewhere on my file system. I'm not paying too much attention to where things end up, but let's say it's gonna be somewhere in the Zephyr SDK folder. Let's see, there we go. I will need to double check that I used the proper command and that it's in the right place. Let's see, Zephyr. Yeah, Zephyr SDK now contains, like, it's a small version, I guess, of the Zephyr SDK, right? Like, but that's enough actually to now just pretend and to tell our environment that we do have a Zephyr SDK somewhere in at this location. And then the environment is basically ready. What I just need now to build an extension is the actual EDK archive corresponding to the host environment, or like to the base application that's meant to be extended. And then I need to write some code. And so I've prepared a repo. For convenience, I've included the EDK in there. And this is how the really basic, how the application would look like if a customer were to write an extension. They don't care about West. They don't care about sample.yaml, blah, blah, blah. They don't care about having a CMake file that references the Zephyr CMake extensions. Like, they most likely, and if possible, they really just want to write code as basic C applications. And that's effectively what you see here. Like, no mention to the Zephyr CMake extensions, a really basic C file, and then some snippets that will be included that just reuse some of the typical compilation flags, which point to where my Zephyr SDK / ARM toolchain is going to be located. So let's move on to cloning this repo in my Docker container. There we go. So what's in there? Exactly what we were just looking at. So the LLEXT EDK, I need to unpack somewhere on my machine. Let's say I'm going to put it in TMP folder. That sounds about right. I don't think we ever looked really into what's the LLEXT archive contents, but I think you can imagine, and I think I've actually sort of mentioned it already a bit, but what's in there is a bunch of C flags to know how to build the application in a way, the extension in a way that aligns with how the host application is going to be built, so that things are actually able to work. And then you would have also, as part of the EDK, header files. Like, there's literally like all the Zephyr header files that the customer might ever need, the header files from all the modules like LVGL in my case, and so on and so forth. So I've unpacked the EDK. Now the only thing I need to do is make sure I add it to my as an environment variable, because the build system for my really basic application expects that LLEXT EDK installed here path to be set, and that's it. I'm basically ready to roll with building my extension. In the build folder, I've asked CMake to do its magic, making and building the extension, and now I have the extension all ready to go. Like, this guy is probably look pretty ugly if I look at it this way, but this is the extension, right? With the few, I mean, it's actually really tiny. Even if we look at it binary wise, we can tell that it's a really small extension that's going to do something, hopefully. And that's something, in order to test it, there is a way which I was demoing already in the previous demo for 3.6, which is encoding it in base64 format, so that we can then use the LEXT shell commands to load it at runtime. Like, this is a nice way during development to test your extension. So let's build and let's convert the LLEXT extension to base64. We want to make sure that it's done in a way where I can easily copy it and actually use it. So that would be apparently my extension. Let's make sure I'm carefully copying all the bits that actually matter, putting them into my clipboard, and then looking at my this is the console, the shell for my STM32 right here. So remember, if I click, it tries to load an extension. Cannot find any right now, but if I am to use the LLEXT shell commands, there is an LLEXT load eggs which expects an extension name, which in my case, if I remember correctly, would be LLEXT, and then the X content of the extension itself. Let's try and load this guy. Done, successfully loaded extension. So now should I click on the button, the extension is available, and boom, that's again, you want to help your customers build extensions for your host application. You don't want to give them access to your source code. You don't want to bother them with having to develop in the context of Zephyr proper, like there might not be any reason to do so. So I think I've shown in real time, like how much time you can save and what this is all enabling. LLEXT is growing really fast in the Zephyr ecosystem. A lot more has actually happened in the 3.7 timeframe. Check out the full release notes, but yeah, that's for one more demo. On the topic of security, there is something that I would like to mention real quick around SPDX, which, in case you're not familiar with, is a standard that allows you to describe in a standard way the software bill of materials for a product. So when for you, what this means is that should a regulation authority or a customer ask you for the very definite, very precise list of all the software components that you might be pulling into the actual firmware of your product, then you're able to provide them with this information in a way, in a standard way, which means that it can then be used in tools to automatically check those components against known vulnerabilities, etc., etc. It turns out that for many years now, Zephyr has been able to provide and to output an SPDX SBOM, and doing so is really easy. You end up using the usual WEST command, except that you would ahead of time indicate that you want to build in a way where SPDX metadata is being gathered from all the metadata available in the build system, getting all the modules pulled in, etc., etc. So this is typically where and how you will build your application. Fast forward to the application being built. Okay, so my application is built, and given that I ahead of time said that I'm interested in getting SPDX output, my build folder, essentially like West and CMake, have gathered all the information needed to effectively generate the SBOM. Like, they kept track basically of all the source files that ended up being linked in my binary, etc., etc. So I can now run the West SPDX command to effectively get the SBOM, or SBOMs rather, actually, corresponding to my application, which I get in my build folder. So let's have a look at them real quick. Without going into details, but essentially this describes for the application I ended up building what were all the source files that got pulled and linked in my final binary, what were their SHAs and checksums and whatnot. So this is really useful information. One thing that's actually new in Zephyr 3.7 is the fact that the list of modules is also being captured. And that's actually quite interesting, in that not only do you get a sense of what were all the modules being potentially used by your application, but there is effectively a way to describe and to add metadata to your Zephyr modules, so that to indicate something that's called CPE, which is effectively the identifier, the standard identifier of the software package that might actually be used in vulnerability databases to identify that the particular component is impacted. So what I mean by that is that, for the sake of the demo, the only thing I did before building this Wi-Fi sample, which hopefully is something that's going to pull in some security stuff, namely embed TLS, the only thing I did is that in my Zephyr 3, I made a small tweak to pretend that the version of the embed TLS module that I would be pulling into my, sorry, I'm not looking in the right place. The version of the embed TLS module that I'm pulling in, I pretended that it is effectively this particular version of embed TLS as per the standard CPE sort of terminology. And this may or may not look familiar to you, but this string, this identifier, is what might be used in CVEs should at some point someone figure out that 3.5.0 version of embed TLS has a security vulnerability. So I pretended that embed TLS is effectively 3.5.0. So somewhere in my SPDX file, this information is probably captured. Well, it is, right? You can see it here. So it's all fine. But what's actually way more interesting is that given that this information has been captured in my SBOM, I can use third-party tools to look and check my, validate my SBOM against common security databases to see, hey, given a list of software modules, am I or am I not in trouble? And so there is such a tool called CVE bin tool from Intel, I believe. It's open source and it relies on databases from HAT and many others. So by running this command line, what I'm going to do is effectively check whether I'm impacted or not. And it should take only a moment. I mean, it can actually take a long time the first time you run it because the databases it uses are huge. It can actually take like an hour to get it set up initially. But what matters is that as I pretended that I'm running on top of embed TLS 3.5.0, there's apparently 4 vulnerabilities I should be aware of, including 3 that are actually high. So I mean, you get the idea. I could obviously just do the quick hack right here, pretend that I'm running on a more slightly more recent version. Let's see if this one is impacted. Maybe not, hopefully not. Yeah, 3.5.2 is clear, and I believe, and I think, Zephyr 3.7 is actually shipping 3.6. So, but we should check that one out. Long story short, should you be packaging your own modules, it might make sense to look at their metadata and do just like I did here, augment them with the CPE should one exist. I mean, of course, CPEs only exist for well-known open source components. But yeah, I think it's actually a quite useful feature and sort of builds on top of the existing pretty nice story that Zephyr has when it comes to SPDX support. Okay, let's talk about power management for a bit, because there's quite a few new features available through the shell that I think are going to help you understand better what happens under the hood when it comes to all things power management, runtime power management, device power management, and yeah, like understanding things better, I think, is usually how I approach the shell. You can start like interacting more directly with all the different subsystems. And in the case of power management, those new commands are also really great help when it comes to troubleshooting and making sure that should you be writing a driver where you really care about getting it right and making sure that you consume as less energy as possible, you get a better, like you have a way to directly interact with your different systems and force them to go to sleep, or the other way around, pretend that they're being used and see what's happening under the hood. So let's just switch to the demo. I have a, I can actually try and show you, but it's probably look terrible. But I have a Nordic power profiler kit hooked up to, where is it? Yeah, whatever, to just a random Zephyr board running the sensor shell. And PM is enabled, power management is enabled, runtime power management is enabled, which means that should the drivers know what to do, there's basically a way for, say, an I2C sensor to tell the I2C bus when it's not needing it anymore, so that potentially when no one needs I2C anymore, then it can potentially go to sleep. So the board is actually an STM32, which is actually quite relevant because I think STM32 is one of those rare platforms where you would have things like the I2C bus implement PM device runtime. Okay, so this is sort of like the standby current consumption for my device. This is the shell. If I start interacting with the shell, it's generating some traffic on the UART and consuming some energy. If I try to run commands, this is consuming energy as well. There's nothing new there. So yeah, I want to show you some of the new commands. So let's see. Some of the new commands, basically, it starts by first like the classical historical device list command. There's something that I think is quite nice that's been added, is that should you have power management enabled in your system, then when you list devices, those devices that have like device runtime capabilities, you are able to see whether at a given point in time they're in use. And it looks like some of the GPIO controllers are actually being used. Yeah, we have probably have an ADC somewhere. We will be playing with the ADC at some point and try and disable it or like put it to sleep forcefully to see if that has any impact on the power consumption. So yeah, let's see right now. So I can trigger and get the sensor to give me some sensor data regularly. It's actually always awake, and it's not really suspended until potentially I use some of the new commands available in Zephyr 3.7 to tell the BME 280 that I would like it to go to sleep. This is really like hardly noticeable because this particular sensor, there's hardly any difference if you look in the data sheet between the idle power consumption and the regular power consumption. But we can do more. We can do things like pretend that because there's several PM commands. Some like resume, suspend are really what's called device power management. So from typically this would be from your application, you know when a particular sensor, when you don't need it, like you know as the application developer that you want to sort of release it, so you would call those PM device APIs. But there's also the more like the runtime APIs that are usually this is happening automatically under the hood for you. Typically whenever the BME 280 I2C sensor requires the I2C bus, it would wake it up by asking to the I2C bus to wake up if it's not already active, and then release it later on. And so I can actually force that, and I can pretend that I want the I2C bus XYZ. I think we're looking at this one, maybe. Let's see. I'm pretending that I'm using it, just like a regular sensor would do. And here we see a noticeable difference. And there could be another device, a second device using it, in which case nothing happens really because the I2C bus is already active. But then I can start releasing, right? And so releasing I2C bus 5800, one device just released it, or supposedly a device. You get the idea. Second device, now there's no one using it, right? And so not only can you exercise your different devices, different IP blocks and peripherals, and see the impact of having one turned on or off, but you can also sort of troubleshoot like a particular device never being released, and etc., etc. And obviously, should I get, let's see, if I get, yeah, this guy 1, 2, 3, 4 times, and then do device list once again, we should find that it's being, yeah, it has four clients or four users at the time. Yeah, let's see. I mean, there's other peripherals which we could probably interact with. I think there's an ADC that's by default that's active to deal with battery voltage and whatnot. Let's see how much can I save if I turn it off. Oh, actually quite a few milliamps, like 0.6 milliamps. That's certainly several months of battery life that you're looking at. So you will probably think twice and be like, hey, maybe I don't need this particular ADC, or I want to turn it off more and more often. You get the idea. Those are all like really nice shell commands. How did I enable this particular demo? Again, this is, I think I started with the sensor shell example and just enabled a bunch of kconfigs for making sure that PM, like device power management, was enabled, device runtime, like power management, and then I think I enabled the I2C shell, which maybe wasn't there, so that I could exercise the I2C commands should I need it, GPIOs, etc., etc. But yeah, that's I think a really nice. I mean, the shell keeps getting better and better. Speaking of which, we're actually going to switch to another demo. Just give me a moment to switch to another device, and we're going to keep looking at the shell, this time over Bluetooth. Right, so shell and Bluetooth and snippets. Actually, one thing that was reasonably recently added to Zephyr is the notion of snippets, which effectively is like you have those overlays and those kconfig options that you tend to always reuse and enable from one project to the other, for enabling a USB console, for having some kind of shell capabilities, like the kind of commands that you always end up using in all your, like when you're debugging a project, commands that or like configuration options that you always end up enabling when it comes to enabling tracing for your application. So snippets provide you with a way to give a name to those overlays and your those kconfig and device tree overlays that you always end up reusing over and over again. And there's quite a few available in Zephyr already. And there's one new, which is building on top of the new. There's a new driver essentially for the Nordic UART over NUS, which makes it possible to have UART and the Zephyr console exposed over Bluetooth. And so demo-wise, what I want to show is just the basic sensor shell example that I deployed on this little guy. So this is a new board supported in Zephyr 3.7 from Croxel. So it's effectively a Nordic chip and a really nice form factor. Coin cell battery, so it might actually be the only demo in this video which is like effectively fully wireless, which is always nice. So this guy is already powered on. I have my phone right here running an application that's going to allow me to, one, scan from for devices and look for devices in proximity. I have quite a few actually, but the one that really matters is the Zephyr device. I'm going to try and connect to it. Let's see. Connected. Oh, that's cool. Let's see. Help. Yeah, that's actually the Zephyr console right here. The full-blown Zephyr console. Let's see. Device list from earlier. I could probably run that guy. Yeah, so that's the list of devices. I didn't enable power management, so I don't have the fancy extra pieces of information we saw just before, but I do have the sensor shell, I believe. So I could probably get info from let's see, the accelerometer maybe. Yeah, let's see. That's actually pretty cool. Let's hold the device right like pretty horizontally, and we have the z-axis which is -1G. Let's flip it around, and I guess we should, yeah, I mean, this is really real time, right? you see that right here, like vertically we have 0. So I mean, this kind of sounds like this is just like for fun, but believe me, there are many situations where you're going to be really happy when your device is out there in the field, and like you have something that's really close to your final design. There's no easy way to access the physical UART on the device. It's probably going to be useful to be able to enable this particular functionality and get basically just the regular Zephyr console, which I mean, here I'm using for the shell. I could certainly get the logs of my application on there as well. So that was for this really quick demo. If you're interested in using the snippet, it's really literally as easy as building your app with the snippet enabled, which effectively is going to pull, and we can have a really quick look at it to give you a sense of what how little is behind the snippet at the end of the day. It really is just basic overlay, both device tree wise, redirecting in this case the console and the shell to the new news thingy, and configuration wise just making sure that we effectively enable Bluetooth, we enable all the BLE options so that the news driver can kick in. But yeah, that's one more demo. All right, yeah, something that I haven't done just yet, because it's actually really hard to keep track and to be sort of exhaustive when covering this. But yeah, it's the sheer amount of new boards being supported and new shields as well. And so I will let you go through the entire list, but it's actually entire SoC series that get added, obviously, from one release to the other, and many new boards all across the spectrum. ARM, RISC-V, lots and lots of new boards and shields as well. And I want to like go just real quick into this field, just to show you one new thing that's going to be worth your while, hopefully, is the fact that yeah, let's pick up this guy right here. So this is we're actually going to real quick see a demo, but there's this fancy round display from Seed Studio, which happens to be supported now in Zephyr, but now adding and enabling a shield in your when you build an app, and stacking a shield on top of your existing device, your board's device tree, can be done with this new West argument, as opposed to before having to pass it through minus a D argument. It's now easier actually to do it, and this particular display, just for the sake of the really quick demo, as I think some people will be interested in seeing it. I mean, nothing incredibly fancy here. It's once again the LVGL default sample, but this is a really nice device with touch support as well, and the actual SoC for folks interested in ESP32 stuff. This one is an ESP32C6, which in the Zephyr 3.7 gets support. So I mean, the combo is really nice, in my opinion. At least you have like a really small form factor, a really sharp LCD. So go and build your next smartwatch on top of either of those. All right, so yeah, as you can tell, there's just so much that went into Zephyr 3.7. Not only is it an LTS, which supposedly is all about stabilization, but it turns out that the community and all the vendors that are heavily committed to Zephyr, they actually did a great job adding tons of really nice features. To name a few more that might not get a proper demo, but I want to call out like the fact that we've started to make some put some effort into documenting better what it takes and how you can use code editors and IDEs such as Visual Studio Code or JetBrains CLion Like you would find lots and lots of blog posts out there, but no sort of like official documentation from the project. So we've started to address that, and go and check out those documentation pages, contribute to them if you find anything missing or wrong. Other interesting work being done around the sensor abstraction model and sensor APIs. I didn't get to really demo it, but I'm hoping we will get a tech talk about it really soon. I could have actually included some of it in the WebSocket demo, if you remember it. Essentially, the idea is that now there is a way to decouple the data acquisition, the raw data acquisition from the sensors, from the actual decoding, which means that it makes it easier to have those DMA sort of scenarios or streaming scenarios where acquiring the data from the sensor is really just one small piece into your entire sensor fusion chain, right? Like you want to feed your raw sensor data into other potentially other algorithms, etc. So you don't really care about necessarily decoding temperature value as like X Celsius. You'd rather feed the raw data into your AI models, your sensor fusion algorithms and whatnot. So that's kind of in a nutshell what this new abstraction model enables. Better throughput, better mapping to modern hardware when it comes to sensors that might have like generate lots and lots of traffic and raw data. What else? Yeah, Bluetooth, same. We will be trying to cover some of the Bluetooth news in a dedicated episode, but LE, the audio stack keeps getting more and more rich. We've mentioned, of course, the UART service with what I think was a pretty nice demo. But yeah, always some really good, cool development on the Bluetooth front. And with that, if you want to learn more and if you want to interact more directly with some of the folks that help make Zephyr happen, which, by the way, I mean, it really takes a village. There's, I think, over 650 people on this release alone who ended up contributing code to the project. But next week, at least if you're watching this as this goes out, we will be hosting on the Zephyr YouTube Zephyr channel a new tech talk where we will basically go through the news, right? And so you can go and check out and subscribe already to this episode on August the 1st, sorry, in the early afternoon European time, early morning Eastern US time. Then yeah, it should be fun. Some people will probably be bringing their own demos as well, so tune into that one as well. The comments are enabled on this video, so any questions you have, any feedback you have, tell me. This is all about the interaction and the feedback in this community. And with that, we will see each other again for a new tech talk, probably for Zephyr 4.0, most likely in a few months. Thanks.